All right, so we're going to talk about 8.5, which the title of it is Random Variable Probability Distribution and Expected Value. We're going to talk mostly about expected value here. So the random variable is just a function that assigns a numerical value to each simple event in the sample space of S. And then with the probability distribution is just the probability of the random variable. For the expected value, the average result you should expect to approximate if you repeated the experiment a large number of times. Just like if we're flipping a coin, we expect with a coin we're going to get heads and tails at 50%, right? But that's if we do it a large number of times. If we just do it a small number, we might get more heads than tails. But if we continue to flip it and flip it and flip it, we should get about a 50% or 1 out of 2 expectation of getting heads or getting tails. A game is fair if the expected value is equal to 0, and it's unfair if it doesn't. The E of x is going to be equal to your x value times the probability, plus the next x value times its probability, plus all the other x's times the probability. So for example 1, if the probability distribution for the random variable x is given in the table, what is the expected value of x? So this is 8.5, and we're talking about expected value. So for example 1, our E of x is going to be our x value times the probability value. So we're going to have -6 times 0.5 plus 4 times 0.3 plus 3 times 0.2. As we multiply these, -6 times 0.5 will get us -3. 4 times 0.3 will get us 1.2. And 3 times 0.2 will get us 0.6. And when we add all that together, we get -1.2. And that would be our expected value for our problem. All right, for example 2, you draw and keep a single bill from a hat that contains a $2 bill, a $10 bill, a $20 bill, and a $100 bill. What is the expected value of the game to you? So again, we're going to do the expected value. So this time we have our E of x is equal to, now this is the value of our x, but what is the probability? We have 1, 2, 3, 4 bills, so we have a chance of getting each one 1 out of 4. So because there's 4 in there, if I put 4 pens in here, the probability of pulling one of those pens is 1 out of the 4. So this will be $2 times 1/4 plus $10 times 1/4 plus 20 times 1/4 plus 100 times 1 out of 4. So 2 times 1/4 will get us 0.5. 10 times 1/4 will get us 2.5. 20 times 1/4 will get us 5. And 100 times 1/4 will get us 25. And when we add all these together, we end up with $33. So what's the expected value we expect to get if we pull out a single bill? The expected value would be 33. And if you're like, but wait a minute, there's no $33 bill. There's a $2, a 10, a 20, and a 100. But over repeating it over a lot of times, not just one time, but remember we talked about the definition. If you repeat the experiment a large number of times, the average of $33 would be the expected value. Okay? All right, let's go on to example 3. In tossing fair coins, what is the expected number of heads in each case? All right, so for example 3, we've got 2 parts. We've got 6 coins and we're going to flip 5 coins. So for part A, our expected value would be 6 is our X. Our probability for getting a head or a tail is going to be 0.5. Sorry, you couldn't see that. So 0.5, and that will get us 3. So the expected value will be 3 for flipping the coin multiple times. And then for part B, our E of X, we are looking at 5 coins. The probability is still 0.5, and that will get us 2.5. So that's our expected value for flipping the coins multiple times. All right, let's go look at example 4. So example 4, we have an unfair coin is flipped. Unfair coin means that it doesn't always do 50-50. It could land on heads more or tails more. If a head turns up, you win $1. If a tail turns up, you lose $1. The probability of a head is 0.66, and the probability of a tail is 0.34. Remember, all the probabilities have to add up to be 1. So let X be the random variable for the amount won on a single play of this game. What's the expected value of the game? All right, so for our expected value, our E of X, if we win $1, the probability was 0.66. And then if we lose $1, so that's winning $1, so you have a positive $1. If you're losing, you're going to lose $1. So losing $1 is 0.34 is the probability of that. So we're going to get 0.66 minus 0.34 when we do our math, which gets us 0.32, and that would be dollars. So basically, you would expect to win 32 cents on the experiment over several times. All right, example 5. We have 2,000 tickets are sold at $1 each for a charity raffle. Tickets are to be drawn at random and monetary prizes awarded as follows. 1 prize of $1,200, 3 prizes of $400, 5 prizes of $60, and 20 prizes of $5. What is the expected value of the raffle if you buy 1 ticket? So, let's go to example 5 on our paper. Oops. One thing we have to remember is that when we look at the outcome, like how much we're gaining, the cost of the ticket is $1. So whatever the prize is, we got to subtract $1 from each one. So the actual winning for $1,200 would be $11.99 because we've got to subtract out $1. For $400, it'll be $3.99. For $60, it'll be $59. And for $5, it would be $4. And then you also have the ability to buy a ticket and then not win anything. So that means you'd lose your $1. Now, here's our key right here. 2,000 tickets are being sold. So we have the number of amount of tickets. So what we're going to do is we're going to create a chart just like we had on example 1 so that we can kind of see what's going on with this. All right, so we're going to have our X sub I and our P sub I. So our X and our probability. So for the $1,200 ticket, the amount would be $11.99 because we have to subtract 1. The probability of that, there was only one opportunity to win the $1,200. So it's 1 out of 2,000. For the $400, the gain would be $399 because they had to pay $1 for the ticket. And there were 3 of those out of 2,000. For the $60 ticket, we would have a win of $59, and there were 5 of those out of the 2,000. And then for the $5 ticket, we would have a winning of 4, and there were 20 of those out of the 2,000. But then what if we just lose? We don't win anything? That would be a negative $1 value. We have 25, 28, 29 tickets that are winners. So 2,000, let me do this in a different color. So 2,000 minus 29 winning tickets leaves us with 1971. So this would be 1971 out of 2,000. Would it be our probability of losing? All right, so now we need to find our E of X. So our E of X, you can change these down to a decimal. Let me put that in parentheses down below or just over. So 1 out of 2,000, we can change it to a decimal if you want to. You don't have to, but I believe that's what your homework did. So 1, oops, clear that. 1 divided by 2,000. We'll get a 0.005. You can change it to a decimal if you want. You don't have to. 0.005. This would become 0.0015. This would be 0.0025. This would be 0.01 and 0.9855. All right, so now we can use that instead of writing the fractions, but you could use the fractions too. It really doesn't matter. So now we'll have 1199 times 0.0005 plus 399 times 0.0015 plus 59 times 0.0025 plus 4 times 0.01 plus we would have negative 1 times 0.9855. All right, so this would get us 0.5995 plus 0.5985 plus 0.1475 plus 0.04 minus 0.9855. And that'll get us a total of $0.40, which is the same thing as 40 cents. So if you played this over and over and over on a large number of them, you would expect to make 40 cents. All right, let's go to our next example. We'll go to example number 6. So for example 6, suppose that each birth having a girl is not as likely as having a boy. Usually we look at having boys and girls. You have a 50-50 chance, just like you do on flipping a coin, a heads or tails. The probability assignments for the number of boys in a 3-child family are approximately from the past records and are given in the table. What is the expected number of boys in a 3-child family? So what we're going to do is, again, multiply our X value times our probability value. All right, so our expected value, our E of X, will be equal to 0 times 0.17 plus 1 times 0.34 plus 2 times 0.37 plus 3 times 0.12. So when we do the math, this will get us 0. Anything times 0 is 0. Anything times 1 will get it what it already is. 2 times 0.37 will get us 0.74. And 3 times 0.12 will get us 0.36. And that'll be 1.44 will be our expected value. And this is the average number of boys. Now, we expect then to get about 1.5. So to me, that if you're talking three-child family, it's pretty close to the half. Now we don't have any half children, right? You're either going to have a boy or 2 boys or 3 boys or no boys, but we're not going to have 1.5 children. That's one thing we don't do in our probabilities. So that's how to do expected value. Take your values times the probability, and then this is what you expect to get over a large number of experiments.